All right, let's take a look at the practice test. For the instructions, we're asked to find the sum of the two complex numbers graphically. All right, for problem 1, we have 7 plus 4i, then plus -5 plus 6i. So for the first problem, let's just take our time and do a little refresher. Before we go to the coordinate plane, let's just think about how to do this algebraically. So first and foremost, we know with a complex number, it's a plus bi, or you could say x plus yi. Okay, either one you want to use. I'm going to stick to a plus bi for right now. Later on, I'm going to change to the x plus yi. Let me write that over here as well. So a plus bi. So we know that a is the real part and b is the imaginary part. So for this first complex number, a is 7. That's your real part. And then b is 4. That's your imaginary part. Over here for the second complex number, a is -5. That's your real part. And b is 6. That's your imaginary part. If you want to add these guys together algebraically, you're going to combine what you can. So in other words, I know that I can add 7 and -5 together. Those are the real parts. So let's go 7 plus -5 like this. And then plus, I know that I can add 4i and 6i together. But the way I'm going to structure this, I'm going to pull the I out. So in other words, I'm going to add the imaginary parts together. So I'm going to go 4 plus 6 like this. And then I'm going to put the I, or the imaginary unit, at the end outside of the parentheses. Okay, so let's just go ahead and do the addition now. So 7 plus -5 is 2. And then plus 4 plus 6 is going to be 10. And then times the imaginary unit I. So notice that with our answer, again, we have the form of a plus bi. So a here, the real part is 2. B here, the imaginary part is 10. So hopefully you already knew how to do that, and it's just a refresher for you. Now what we want to do is graph these guys as what we call position vectors, and then find the sum graphically. So let me go ahead and erase all of this, and I'm just going to write that we have 7 plus 4i, and then plus this -5 plus 6i, and this should give us 2 plus 10i. So let's grab this real quick and let's just paste this in right here. So looking at this right now, you already see a little drawing, and I'm just going to walk you through where this came from, and I'd like you to make this on your own as well. So first off, when you work with complex numbers, again, we say a plus bi, where a is the real part and b is the imaginary part. Now on a coordinate plane, typically the x-axis is the horizontal axis, but now we're going to say this is going to be the real axis. So if we're looking for something with a, the real part, we're looking for this on this x-axis, or now the real axis. Now the y-axis, or the vertical axis, we're going to call that the imaginary axis now. So if we're looking for something with b, we're going to be looking along this axis here. So if I think about this first guy here, this 7 plus 4i, well, 7 is the real part and 4 is the imaginary part. So in other words, it's just like I said, I want to go to 7, 4 on the coordinate plane. I want to go 7 on the real axis, and I want to go 4 on the imaginary axis. So 7 units to the right and 4 units up, that puts me right there. So if I wanted to plot the point 7 plus 4i, that's where I'd be. Now the other guy, I have -5 plus 6i. So -5 is the real part, so I'm going 5 units to the left, and then 6 is the imaginary part, so I'm going 6 units up. So it's a little bit covered up. Here's 3, 4, 5. This would be 6 right here. So from the origin, I could go 5 units to the left and 6 units up. So right there. Or you could have also started here and went 6 units up and then 5 units to the left. Either way, you get to the same point. Okay. So now we have our points there. And basically, you're going to sketch these guys as what we call position vectors, where those points that we labeled are going to be the terminal points. When you have a position vector, remember, the initial point is at the origin, or 0, 0. In this case, you could really say that the origin is 0 plus 0i if you wanted to. All right, so thinking about it, we have this vector and we have this vector. Now, what you do is you can take this guy right here and slide it down to create this side right here. So in other words, if I wanted this vector here to slide down, starting from this point right here as the initial, well, now I just use these coordinates here. I want to go 7 units to the right and 4 units up. So from right here, if I go 7 units to the right and 4 units up, I'm going to end up right there at my 2 plus 10i, or my sum. To create this side right here, all you're going to do is slide this guy down, right? So in other words, starting here, I want to go 5 units to the left and 6 units up, just using these coordinates here. So 5 units to the left and 6 units up. Again, I get to that point. So this just completes a parallelogram. So that's one way that you can do it to get this, what we call resultant vector, where the initial point is at the origin and the terminal point is going to be at that 2 plus 10i. So that's how you can show that graphically. Now, another way that you could have done this, again, with the triangle method, let's say you sketch this guy first. Well, instead of sketching this guy in standard position, you could have sketched this guy like that, okay? And then essentially your resultant vector, it's got the origin as its initial point, and it's got this terminal point here. So in other words, that's how you can complete this with the triangle method. You could have also done it a different way. You could have sketched this one first like this, and then sketch this one like this. And again, it's the same resultant vector either way. All right, let's take a look at problem number 2. So here we have -7 minus 7i, then plus 6 minus 4i. So again, before we go to the coordinate plane, let's just add this algebraically. So we know we would add the real parts together. So -7 plus 6. Let me write that out. So -7 plus 6. And then basically you're going to add this -7 plus this -4. So let me write that. So -7 plus -4. And then times that imaginary unit I. So I'm just pulling it outside of some parentheses here. Let me go ahead and say this equals -7 plus 6 is going to be -1. And then plus, you have -7 plus -4, that's -11. Let me just write -11. And then times the imaginary unit I. So this is what we're looking for. Let me get rid of this. Let me actually just rewrite this so we can copy it. So -7 minus 7i. And then plus, we have 6 minus 4i. This would be equal to this -1 minus 11i. So let me paste this in here. So again, all we're using here is what we call the parallelogram method. And so starting at the origin, or 0, 0, I would sketch a position vector. Let's just start with this one. Again, it's -7 minus 7i. So I'm going 7 units to the left on the real axis. So that's right there. And then 7 units down on the imaginary axis. So that's going to put me right there. Okay, let me show that right here. And it's a little bit hard to see, so maybe I can do this in a different color. In other words, from the origin, you can either go 7 units down and 7 units to the left, or you can go 7 units to the left and 7 units down. Either way, you get to that point right there. Okay, now that we have that guy, again, you can sketch that little vector right there. And then for this guy, we have 6 minus 4i, so that's going to be your terminal point there. So again, from the origin, you're going 6 units to the right and 4 units down to get to that point right there. Just like we saw last time, we're going to take this guy and slide it down, okay? So from this point right here, if I'm thinking about it, I'm moving 7 units to the left and 7 units down. So if I do that, I'm going to end up right there as the terminal point, okay, when I sketch this side right here. And then additionally, if I want to do this, well, starting here and going there, well, all I'm doing is I'm copying this right here. So from this point right here, I'm going 6 units to the right and 4 units down. So from here, 6 units to the right and 4 units down puts me right there. This guy right here is going to be my resultant vector. Okay, so that's how we would draw that. Now again, if you don't like the parallelogram method, a lot of people don't, you can just use the triangle method. So you sketch one of these. Let's just say you sketch this one, and then you take this guy and you sketch it like this. So that gives you the terminal point for the resultant vector. And this right here would be the resultant vector, how you could form that. Again, you could have also done it the other way. So you could sketch this one first like this, and then sketch this one like this. And then there's your resultant vector like that. So however you want to show this, a lot of teachers will ask you to show this graphically. All right, for the next few problems, the instructions tell us to convert each from polar form to rectangular form. So for problem 3, we have 5 times. So our quantity here is the cosine of pi over 4 plus you have I, that's the imaginary unit, times the sine of pi over 4. So to solve this problem, just first think about what is the cosine of pi over 4, or 45 degrees. Let me write the cosine of pi over 4. This is square root of 2 over 2. And then the sine of pi over 4 is also square root of 2 over 2. So I'm just going to replace the cosine of pi over 4 and the sine of pi over 4 with square root of 2 over 2. So let's say this is 5 times the quantity. You have square root of 2 over 2, then plus square root of 2 over 2 times I. Now sometimes we'll put the I right here. But again, a lot of this is just going to be personal preference. I like to stick it out here. Okay, so now what I'm going to do is just multiply this 5 by each guy here, right? So in other words, you're just going to distribute it. So this would be 5 times square root of 2 over 2, and then plus 5 times square root of 2 over 2 times your imaginary unit I. And again, some people will like to write it like this, just in case you see it. So you might see 5i times square root of 2 over 2, but I'm just going to keep it like this. So this right here would be my rectangular form. All right, let's take a look at problem 4. So here we have 3 times the quantity cosine of 7 pi over 6 plus I times the sine of 7 pi over 6. Okay, so thinking about this again, what is the cosine of 7 pi over 6? And then what is the sine of 7 pi over 6? So you can use your calculator if you want, but I think at this point in the course we should know what 7 pi over 6 is. If not, you can always convert it. So remember, you can multiply by 180 degrees over pi radians. So this will cancel. Then 180 divided by 6 would be 30. So 7 times 30 is going to be 210. So this would be 210 degrees. So remember, with 210 degrees, you have a reference angle of 30 degrees. And you're going to be in quadrant 3. So this is equal to, in quadrant 3, cosine is negative. So this is the negative of the cosine of 30 degrees. So this is negative square root of 3 over 2. And this right here would be, since I'm in quadrant 3, I'm also negative. And then it's the sine of 30 degrees, which is a half. Okay, so thinking about this, we come down here and we say that this would be 3 times, I'm going to replace this with negative square root of 3 over 2. And then plus, I'm going to put negative 1/2 here times my imaginary unit I. So let's say equals, just distribute the 3 to each guy. So we'll say this is the negative of 3 times square root of 3 over 2. And then basically you can just put minus, the 3 is going to be distributed. So 3 times 1/2, which would be 3 over 2, and then times I. So this guy in the end would be negative 3 times square root of 3 over 2 minus 3/2 I as your standard form, or again, some people call this the rectangular form. All right, for the next few problems, our instructions are going to change. Now we want to convert each from rectangular form, again, that's also called standard form, to the polar form. Now for problem 5, we're given the complex number negative square root of 6 plus I times square root of 6. Now this is something where if you're struggling, just make a sketch. So in other words, you would want to sketch this complex number as a position vector. So the terminal point would be at negative square root of 6, comma, square root of 6. So this is your real part, and this is your imaginary part, okay? So we can write this as a plus bi, or in this case, you see the I is switched around, so a plus ib. A lot of books also start using x plus iy, or x plus yi. And I'm going to actually stick to this notation here for the remainder of the course, just because the book I'm using is going to switch it up. So I'm just going to stay consistent with them. Let me grab this real quick. We'll actually come back here in a moment. I'm just going to put equals and then head down here. And I'm going to paste this in. So you see that I already have this over here. I just wanted to show you where it was coming from. So essentially with this complex number, again, I'm going square root of 6 units to the left and then square root of 6 units up. Remember, this right here is the real, this right here is the imaginary. Okay, so once we've sketched this as a position vector, how can we write this in polar form? Remember, this is r, which is the length of this vector, or you could say the magnitude. It's also the absolute value of that complex number, or what we call the modulus. So this times the cosine of theta, and then plus I times the sine of theta. So you've got to figure out r, or that length there, and you've got to figure out this theta, or the direction angle here of this position vector. Okay, so the first thing is for r, we know it's a very simple formula. So r is equal to what? It's going to be, again, the principal square root of negative square root of 6 squared. This is your real part. And then plus your square root of 6. So your square root of 6 squared, that's your imaginary part. So the real part squared plus the imaginary part squared, that's underneath your square root symbol. That's how you get your r. Again, you can always make a little right triangle and think about this. Let's just say generically that this is going to be x and this is going to be y. Well, again, this is x squared plus y squared equals r squared. Let's just go ahead and see what this is. So r is equal to the square root of the negative of the square root of 6 squared would be 6. And then plus square root of 6 squared would be 6. 6 plus 6 is 12. And 12 is 4 times 3. Okay, so 4 is a perfect square. 4 is 2 times 2. So we can say that basically this is 2 times square root of 3. So that's going to be my r value. Okay, let me get rid of this. And let me write 2 times square root of 3 here. And actually, I'm just going to temporarily get rid of this and erase this also. Come up here and put 2 times square root of 3. And actually maybe drag this down here. and put these parentheses here. So we'll put cosine of blank, theta goes there, plus I times sine of blank. Okay, so we need to figure out what is theta. Now this is the part that's a little bit tricky and where a lot of students get lost. So basically, your book is going to tell you that the tangent of theta is equal to y, which is your imaginary part, over x, which is the real part. So in this case, y is square root of 6. So this is square root of 6. And x is the negative of the square root of 6. So obviously we can cancel a common factor of the square root of 6, and this gives me negative 1. So the tangent of theta is equal to negative 1. Now, the problem with this is, if I use my inverse tangent function, and I plug in a negative 1 there, I am going to get negative 45 degrees, or negative pi over 4 radians. So what it's giving me is this guy right here, and that's rotating clockwise. So this is negative 45 degrees. So you can sketch this out and just think about this mentally. What would I need to do to get from right here to right here? Well, I could just add 180 degrees or a straight angle. So I could say that theta is equal to this negative 45 degrees plus a correction of 180 degrees, which would give me the correct value of theta of 135 degrees. Now that's one way to do it. Another way to do it, which a lot of students find more comfortable, I'm just going to get rid of all this. We know at this point that theta is 135 degrees. You could just plug into your calculator the inverse tangent of 1. Forget about the fact that it's negative 1, just go with the positive, and that is going to give you 45 degrees. So this right here would be the reference angle for your angle in quadrant 2. So you go into quadrant 2 and say, okay, what angle is going to have a reference angle of 45 degrees? Well, it's going to be a 135 degree angle because you do 180 degrees minus 45 degrees to get to 135 degrees. So that's another way that you could have done it. So either way, we come back up here. This would be 135 degrees, and this would be 135 degrees. So in polar form, this is 2 times square root of 3 times the quantity. You can have cosine of 135 degrees plus I times the sine of 135 degrees. Again, you can write this as 2 times square root of 3 times the CIS, and then 135 degrees. This is the shorthand. So the C for cosine, the I for the imaginary unit I, and the S for sine. Okay, so that's 2 times square root of 3. You could say CIS 135 degrees. Okay, let's take a look at problem 6, and here we'll go a lot faster. So 2 plus 2i times square root of 3. We want to write this in polar form. So this is some r value times the quantity cosine of theta plus I times the sine of theta. So I just write my formula out first, and then I think about, okay, well, what's the r value? So r is equal to the principal square root of the real part squared. So 2 squared is 4, then plus the imaginary part squared. Here it's tricky. You have this 2i times square root of 3. Take everything away that's not the I, okay? So you want 2 times square root of 3, and you're going to square that. 2 squared is 4. Square root of 3 squared is 3. So 4 times 3 would be 12. So this right here would be 12. 4 plus 12 is going to be 16. And so the square root of 16 we know is going to be 4. So we can just put this in here as a 4. If we want to get our theta here, which is the argument, or again, as a position vector, you could say it's the direction angle. Let's go ahead and sketch this guy. So 2 plus 2i times square root of 3. Your terminal point would be 2 units to the right on the real axis, and then 2 times square root of 3 units up on the imaginary axis. So right there, there's your complex number sketched as a position vector. And we know that we're in quadrant 1 here. Okay, that's our theta. And so this is very easy. We can just use our inverse tangent function, and there won't be any problems. We'll say that theta is equal to this. And so we're going to do imaginary over real. Okay, so y over x or b over a or whatever notation you're using, just remember imaginary over real. So 2 times square root of 3 over 2. The 2's are going to cancel, and so this just becomes square root of 3. So this is square root of 3. Close that down. You can key that into your calculator, but I think most of you know this is going to be 60 degrees. So let's say this is 60 degrees, and you can put that in there. This equals 60 degrees, and we'll just come back up, and I'll just erase this and just put 60 degrees and put 60 degrees. Let me make that 0 a little bit better there. And you could also write 4 CIS 60 degrees like that. Again, that's coming from this right here, and this right here, just an abbreviation. So 4, you could say CIS 60 degrees. All right, let's take a look at problem 7. So here we have negative 3 times square root of 3 plus 3i. So again, I'm going to write this as r times the cosine of theta plus I times the sine of theta, where r is equal to the square root of, take your real part and square that, so negative 3 times square root of 3 squared, then plus, we're going to take the imaginary part, it's just the 3, and square that. So this right here, the negative goes away. 3 squared is 9. Square root of 3 squared is 3. So basically, this is going to be 9 times 3 or 27. And then this is plus 3 squared is 9. So what is 27 plus 9? That's going to give me 36. And the square root of 36 is going to be 6. So let's say that r here is 6. So I'll just put that in here. And again, we'll just go to the coordinate plane and look at a little sketch. We're going to go 3 times square root of 3 units left, and then 3 units up from the origin. So again, from the origin, 3 times square root of 3 units to the left, and then up 3. So let's say that puts us right there. So this is going to be our complex number sketched as a position vector. We're trying to figure out this angle right here, theta. So again, the tangent of theta is equal to your imaginary, which is 3, over your real, which is negative 3 times square root of 3. And so let's think about this. So this 3 would cancel with this 3. And so what I have is, let me put a 1 up here, the negative of 1 over square root of 3. And of course, you'd rationalize the denominator, so times square root of 3 over square root of 3. So this becomes the negative of the square root of 3 over 3. Okay, let me get rid of all this. So let me put the tangent of theta is equal to the negative of the square root of 3 over 3. So let me do tangent inverse of negative square root of 3 over 3. So a lot of you know that for the tangent of 30 degrees, it's square root of 3 over 3. I think that's a commonly known fact. If you don't know it, it's not that big of a deal. If you key this into your calculator with the negative here, you're going to get negative 30 degrees, or negative pi over 6 if you're working with radians. So you're going to get something like this. So this is negative 30 degrees. So you could just add 180 degrees. So I could say that theta is equal to negative 30 degrees plus 180 degrees, which would give me 150 degrees. So that's one way you could do it. Again, the other way you could have done this, let me get rid of this. You could have just said that the inverse tangent of square root of 3 over 3 is 30 degrees. So that's my reference angle in quadrant 2. So this angle right here would be 30 degrees. So basically, you would go 180 degrees minus 30 degrees, and that would give you 150 degrees. So again, theta is going to be 150 degrees here. Coming back up, let's get rid of this and get rid of this and put 150 degrees here and 150 degrees here. And so we'll go 6 CIS and then 150 degrees. So that's another way you can do it. Again, this C is for the cosine, the I is for the imaginary unit I, the S is for the sine. So 6 cis 150 degrees if you want the shorthand. All right, let's take a look at problem 8. So here we have 3 times square root of 3 over 2 minus 3 halves times I. So I want to set this up as R times, in the parentheses, we have the cosine of theta plus I times the sine of theta. Okay, so let me first figure out what is R. So this is the principal square root of, you have your real part, some people call this A, some people call this X, squared. So let's go ahead and say this is 3 times square root of 3 over 2 being squared. Then plus your imaginary part, again, some people call this B, some people call this Y. So this is negative 3 halves, and you can take the sign with you if you want to make that crystal clear. So this is negative 3 halves, then being squared. Okay, so 3 squared is 9. Let me get rid of this and write this as 9. Square root of 3 squared is 3. And then 2 squared would be 4. So essentially, this is going to be 27 over 4 like this. Over here, the negative would go away. 3 squared is 9. 2 squared is 4. So this would be 9/4 like this. And essentially, if you add 27 plus 9, that would be 36. Put that over the common denominator of 4. So we know that 36 over 4, that's just going to be 9. And the principal square root of 9 is 3. So the value for R here is 3. So let me put that in here. Maybe I'll make that a little bit cleaner here and just put this as 3. And actually, let me get rid of this. I'm just going to drag this down here just so we have a little bit more room. And maybe I'll just rewrite this. So this is the cosine of theta. I'll just put blank plus I times the sine of theta. I'll just put blank and then close that down. So if you make a sketch of this guy, you can see you're going to be in quadrant 4. From the origin, you're going to the right by 3 times square root of 3 over 2, and then you're going down by 3 over 2, or 3/2. So that gives you a terminal point for that position vector that represents your complex number of 3 times square root of 3 over 2, and then comma negative 3/2. So that's where you're going to be there. If we want to figure out this guy right here, that's going to be my theta now. How do we do this? Well, again, the tangent of theta is going to be equal to, you can go y over x, or you can go b over a, however you want to think about it, but it's basically just the imaginary, so negative 3/2, over the real, which is 3 times square root of 3 over 2. And so this guy right here is going to be equal to negative 3/2 times, I'm going to take the reciprocal of this, so 2 over 3 times square root of 3. So this is going to cancel with this is going to cancel with this. So basically, this is negative 1, let me put a 1 up there, over the square root of 3, which we know if we multiply by the square root of 3 over the square root of 3, this becomes the negative of the square root of 3 over 3. So we saw this earlier in the practice set. We know that if we do the inverse tangent of this guy, we're going to get negative 30 degrees. Let me clean this up. So if I go inverse tangent of this negative square root of 3 over 3, I'm going to get negative 30 degrees, or negative pi over 6 if you're working with radians. So that would actually give me this guy right here, rotating clockwise, so that's negative 30 degrees. So basically I have the same terminal side, but what I would want to do is add 360 degrees and just get the coterminal angle. So negative 30 degrees plus 360 degrees would give me 330 degrees. So that would be my correct angle for theta here. So this, swinging around, would be 330 degrees. Again, the other way you could have done that, you could have just plugged in square root of 3 over 3 into the inverse tangent function. You would have gotten 30 degrees. And so now you could say, well, I'm going into quadrant 4. I want a 30-degree reference angle. So 360 degrees minus 30 degrees is 330 degrees. So that's another way you could have done that. So coming back up, let's just put 330 degrees in there and 330 degrees in there. And again, we can go 3 CIS, or CIS, if you want to say it that way, 330 degrees for the abbreviation. All right, let's take a look at problem 9. So here we have negative square root of 21 over 2, then plus 3 times square root of 7 over 2 times I. Okay, so let's go ahead and say this is equal to, we'll go R times, again, inside of parentheses, the cosine of theta plus I times the sine of theta. Okay, so for R, again, all it is the square root of the real part squared. So let's go negative square root of 21 over 2 being squared. Then plus, you're going to take your imaginary part, so 3 times square root of 7 over 2, and that would be squared. So for this guy right here, the negative would go away. Square root of 21 squared is 21. 2 squared is 4. So this becomes 21 over 4. Then for this guy, 3 squared is 9. The square root of 7 squared is 7. So you would have 9 times 7, which is 63. And then this would be over 2 squared is 4. So if I add 21 plus 63, that's going to give me 84. So this would be 84 over 4, and that's going to give me 21. Now 21 is 7 times 3, so I really can't do anything with this. I would just go up here and say that my R value is going to be the square root of 21. All right, for theta, again, we can always make a sketch. So from the origin, we're going square root of 21 over 2 units left, and then 3 times square root of 7 over 2 up. So my terminal point for this position vector that represents this complex number is going to be right there. So this is the angle that I'm looking for. So that's my theta. So again, we can say that the tangent of theta is equal to imaginary over real. So we'll say 3 times square root of 7 over 2, then over, I'm going to go negative square root of 21 over 2. Let's multiply by the reciprocal. So let's bring this up here and say this is negative 2 over the square root of 21. I'll just get rid of this. And so this is going to cancel. And then I can break this up actually into the square root of 3 times the square root of 7. And so I can cancel this square root of 7 with this square root of 7. So what does that give me? It gives me negative 3 over the square root of 3. If I rationalize the denominator, so times the square root of 3 over the square root of 3, this gives me the negative of 3 times the square root of 3 over 3. The 3's would cancel, And so this ends up giving me the negative of the square root of 3. So let me get rid of this and just write the tangent of theta is the negative of the square root of 3. All right, so let's go inverse tangent of, again, you can do it as the negative of the square root of 3. You're going to get something in quadrant 4 going clockwise, and this is going to give us negative 60 degrees. So again, that's going to be this guy right here, rotating clockwise. So this is negative 60 degrees. So once again, if you want that angle, just add 180 degrees. So you can say that theta is equal to negative 60 degrees plus 180 degrees, which is going to give you 120 degrees. The other way you could have done this, you could have said, okay, well, if I plug this in as a positive, the inverse tangent of the square root of 3 would give me 60 degrees. So I'm just trying to find an angle in quadrant 2 with a reference angle of 60 degrees. So that would give me a 120 degree angle. So coming back up, this right here and this right here, we're going to write in 120 degrees like this. And again, for the shortcut, you can go square root of 21 and then CIS. So again, C, I, and then S, and then take your angle, so 120 degrees. Okay, for problem 10, we have negative 3 minus 3i. So again, to convert this over, first I need my r value. So r is equal to the square root of, you take your real part, so negative 3, square that, plus your imaginary part, which is also negative 3, square that. So negative 3 squared is 9 in each case. 9 plus 9 is 18. And so for this, I would break it up into 9 times 2. Square root of 9 is 3. So this would be 3 times square root of 2. Let me get rid of this. So then this is times the quantity. Let me actually move this down so we have room. So the cosine of theta plus I times the sine of theta, and close that down. So this guy right here, if you sketch it, you're going 3 units to the left and 3 units down. So this right here would be the terminal point for your position vector when you sketch your complex number. So I want this angle right here. That's going to be in quadrant 3. So this is going to be my angle theta. So we'll say the tangent of theta is equal to, you have your imaginary over your real. So negative 3 over negative 3 would obviously be 1. So we know that the inverse tangent of 1 is going to give us 45 degrees. So what's happening is we're getting this right here. So it's giving us this piece right here. So it's saying this is 45 degrees. So again, what you need is to add this right here, which is a straight angle to this. So that would be 180 degrees. So you can say that theta is equal to 45 degrees plus 180 degrees, which is going to give you 225 degrees. Now, the other way you could have done this, you could have gone into quadrant 3 and just said, okay, well, I want a reference angle of 45 degrees. So that's going to be this angle right here. That's 45 degrees. So you take your straight angle, which is 180 degrees. That's this piece right here. And then you add the 45 degrees to that. And that gives you your 225 degrees, or an angle in quadrant 3 with a reference angle of 45 degrees. So coming back up here, let's put 225 degrees here and 225 degrees here. And again, we can shorten this and say 3 times square root of 2. And then you go CIS. So CIS or CIS, and then 225 degrees. Let me maybe make this S a little bit better.